My name is Bethany Ellman, and I am director of the Keck Institute for Space Studies here at Caltech. We are a think, do tank designed and created to convene experts from around the world to dream up what does the next generation look like in exploration of space. Whether that's looking down on Earth, looking out into the universe with telescopes, exploring with the best of our engineering. We convene experts, and as part of this, we're having a workshop here on exploring particle environments around other suns. But I'm really here simply to introduce one of our KISS affiliates. We run a program for Caltech students and postdocs to introduce them to this amazing world of space exploration. So it's my pleasure to introduce Dr. Nyati Desai, recently PhD minted from here in Galactic, who just defended her PhD on coronagraphs to help us find Earth-like planets around other stars. So without further ado, Dr. Desai will introduce Dr. Green.
Thank you, Bethany. It's a really kind introduction. Thank you to everybody here joining us today for today's KISS lecture. It's the first one in a while, so it's really great to see so much turnout. It's my honor to introduce our speaker for today, Dr. Jim Green. Dr. Green is a former NASA chief scientist, and his career of 42 years at NASA has been pivotal in shaping our understanding of the universe. He received his PhD in physics from the University of Iowa and moved on to work at Marshall Space Flight Center, Goddard Space Flight Center, and NASA headquarters. With a career spanning over 4 decades, he was the longest-serving director of the Planetary Science Division and has been at the forefront of many groundbreaking missions, including the landing of the Mars Curiosity rover, the Juno mission to Jupiter, and the New Horizons flyby of Pluto. Throughout his time as a scientist, he has written over 125 scientific articles and over 80 technical and popular articles. But in addition to his scientific and administrative roles, Dr. Green has also had a prominent voice in bringing space science to the public. In 2015, he coordinated NASA's involvement with one of my all-time favorite science fiction films, The Martian. He also has been the host of the popular NASA podcast Gravity Assist, which is actually making a comeback, so stay tuned for that. It's going to be coming out again soon. Gravity Assist is an interplanetary talk show where Dr. Green shares insights into NASA missions and the wonders of our solar system through interviews of dozens of planetary scientists, engineers, and others dedicated to missions of NASA for space exploration. Throughout his talk show and many of his public talks, he has made complex scientific concepts accessible and engaging to a broad audience, fostering a deeper appreciation of the mysteries of space like we will be doing today. Last thing, I have to mention a fun fact about Dr. Green. Apart from bringing planetary science and its mysteries to us, he is also a total Civil War nerd. More specifically, he's a bit of an expert on Civil War ballooning. So if you get the chance to catch him after today's talk, feel free to ask him about his involvement and help in the construction and the flight of the world's first replica of a Civil War crewed balloon. Now, without any further delay, I hope you're as excited as I am to hear what Dr. Green has in store for us. Please join me in welcoming Dr. Jim Green.
Thank you very much. Thank you very much. Thank you. Well, it's just a delight to be here, and I'm going to try to tell you everything I know about the origin and evolution of life, not just here on Earth, but what we might find beyond Earth, in the solar system, and beyond the solar system in our galaxy. Now, I would just love to be able to tell you we have found the spark that took non-life into life, but we haven't. We are on the search for that. And you may be surprised at where we need to go to find that information. So we're going to talk about that in the context of the evolution of potential life in our solar system and beyond. But to do that, what we're going to do is we're going to start out with a nice definition of what life is. In fact, when I first became head of Planetary in 2006, I asked my astrobiologist, the lead of that program in planetary science, give me a definition for life. And in about a year later, after all kinds of discussions and debates and conferences, she came back into my room, Mary Wojtek, and said, okay, I think we've got it, okay? Because, life can be complicated. We only know life that's carbon-based, but there could be life that's not carbon-based. So we really want to be able to have a general definition of it that we can go out and make measurements looking for it in our solar system. That's what I wanted. So she came back and said, life has 3 attributes. It metabolizes. So that means with material and liquid, that is a solvent that takes out the food, and then the water or whatever that liquid is used to eliminate the waste. That's part of the metabolic process. It needs a liquid. And then she said it reproduces and evolves. She was happy, and I can't tell you how depressed I was. I can't build an instrument in planetary science that goes out and looks for reproduction or evolution. So we began the process of really concentrating on the first one, metabolism. And now we know here on Earth that life requires water, so let's follow the water. It's very logical when you think about it, because if you're going to look for the origin of life, it's got to have all the right stuff, all the right resources. And of course, our evolution of our solar system, the chemistry of life comes from space. It's all around us as we observe molecular clouds with complex organic molecules and all kinds of stuff that we're finding that's so important for life. And so, in reality, what happened on Earth could actually happen in many other places. So we're on the hunt for those places. We want to know where they are. We have to use what we know about the environment that we have this life and other potential life environments and find those elsewhere as candidates for finding life beyond Earth. Okay, so the ingredients of life then, we need the water. It's part of the metabolism process. You've got to have the organics. That's what you're going to ingest, you're going to extract. For us, it's carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And we have a nice little acronym. It's CHNOPS, CHOMPS. But we have to have energy. You've got to have the right temperature to keep the organics in their volatile state. Okay, this is really important. But we forget sometimes one of the key things that we're finding out is we really need time. It's time with all the right stuff that's in that environment that ends up, we believe, with the possibility of that spark happening and life emerging, okay? So how did that happen? Well, we'll start with our own solar system. This is a very common approach that planetary scientists do. We have a cloud. We believe a supernova exploded nearby that caused the cloud to start collapsing. And therefore, as it spun, saving angular momentum, it created a disk, and out of the disk, planets began to emerge. So you start from dust accretes into larger and larger objects, and you end up with planets at various distances. And in many ways, as you run around the star and scoop up material, the size of these bodies are going to be bigger because you have a larger reservoir of material to scoop up. So we're finding terrestrial planets close to the star, our sun, and more gas giants as we go further away. But we really needed to take a better look at this whole process. Planetary scientists look at that in isolation, and that's wrong. Here's a simulation where we have many stars that are going to be accreted out of this nebula. Well, what's happening to these stars as they accrete? They get gravitationally attracted to one another. And as you can see, they're doing dances all over the place. We know our Oort cloud, the furthest set of cometary material, is a light year or so away from our sun, and stars have gone by that. We've literally shared spit with other stars. All these stars in this area have the same basic material that we did. Many years ago, we thought there was, well, maybe 200 stars were generated in this event. But we now know, more research has told us, it might be anywhere from 2,000 to 20,000 stars. A huge number of stars could have been generated. Well, what happens during this time period is stars move in and out and planets are being created. You have the opportunity to pull planets out of the solar system, okay? And these are typically going to be the large ones that are further away from the sun. And you end up with planets roaming around in the galaxy without stars that they're orbiting. They're actually orbiting the center of the galaxy. And we call those rogue planets. So we now believe there are more rogue planets than there are stars in our galaxy, okay? Now, we've been looking for planets, and we have several techniques, and I'll talk about just a few of those. But we also know there's more planets than there are stars in our galaxy. That's the current estimate. So now we have a huge population to look at and study and try to figure out what are the conditions that really make life happen. Well, that means we really have to look at what we have here at home. What we have here at home is our own star, the sun. So as the sun comes together, and it begins the process of converting hydrogen into helium in its core, it actually brightens over time, very slowly. It evolves over time. So this is a curve of the sun's brightness over time. The dotted line is 4.6 billion years, okay, and that's where we are. So we're on that curve right there. So since the sun really started burning this fuel, becoming the star we know today, it's actually increased in brightness by perhaps as much as 30%. We also know that the sun has been angry in the past. Okay, I mean, we think we see sunspots, it goes through these cycles, it's fantastic. My colleagues are here studying what we know about the sun today, but we really need to be thinking about suns like ours that are in different portions of their evolution, that are down here in the angry stage. This sun is really spinning fast. It's generating enormous magnetic fields, which kick out flares all the time, coronal mass ejections. And how does that affect the evolution of life on the planets that are in that solar system? And that's what we're trying to do. Okay, that's what we're trying to figure out. One of the basic properties when astronomers started to look at finding planets around other suns is to get a gauge on what planets are more important than others, all right? What planets are in the right place where the sun, their star rather, is producing enough energy for water to stay on the surface of that planet, okay? And even better if it stays in all three phases. Liquid, vapor, solid, okay? Just like Earth. Well, they called that area around that star a habitable zone. Now it turns out it doesn't mean that any planet in that zone has got life, okay? But it gives us an indication of where to start looking for. Now, here we are when the sun was very intense in terms of its magnetic activity, but not very bright, as we see early on. That means its habitable zone is very close to the sun. And over time, that habitable zone moves out. So where is the Earth today? The Earth today sits very nicely in the habitable zone. Mars is too cold, Venus is too hot, we're right in the middle, okay? And it's taken us 4.6 billion years to get there, all right? So the evolution of the sun and the evolution of what happens on our planets is intimately tied together, and we're going to try to tease some of the important things out of that to then use that to look for life beyond Earth. Okay, let's talk about our planets. Okay, Mercury. Mercury's bigger than the moon, but it looks like the moon, doesn't it? Here, it's almost what we call tidally locked. It's so close to the sun that the sun's got a grip on it gravitationally that it just barely turns as it goes around the sun, creating a year. So it orbits the sun in 88 days, and 1 day on Mercury is 59 Earth days, okay? Like our moon, one orbit around the Earth is about a month, and that's what its day is about a month. That is tidally locked, okay? Mercury is nearly tidally locked. We have to consider planets that are close to our suns, or their suns, those stars. That concept of tidally locked has got to be an important element of what we know about these planets, and then put that in the consideration of whether we could find life on them or not. Venus is our next one. This is our sister planet, okay? It's a really fantastic planet, but kind of weird in a number of ways. This is what we see in visible light. It's hard to get below the surface to look at it, but we've done that with radar. We have a really good idea what the surface of Venus looks like. It's almost tidally locked too. So, okay, those are wrong. Some cut and paste didn't happen right. So on the order of 240 days is an orbit around the sun, and Venus takes about 250 or close to that. It's not tidally locked, but it's nearly that. All right, so now we know Venus also has gone through some sort of process for which tidal locking may be an important element of that. That's a concept we need to think about what's going to happen to Earth. All right, well, what do we really know about Venus? Well, when we study it and we can look at the surface through radar that penetrates through the clouds, and we can see a fabulous structure. It looks very volcanic in nature. In fact, there are some really hot spots that when we map them to the surface, they map to hilly regions, okay? So we think these are volcanic. Venus is kicking out volcanic material like crazy, and that's what's dominated its atmosphere. And it's primarily CO2, which we know now is a greenhouse gas, and that means light from the sun penetrates through the clouds, gets to the surface, heats it, creates infrared radiation that the CO2 won't let out. You all experience that around here when you get in a car during the summer. Same basic concept. Light comes in through the opaque window, and what happens is that you heat up your seats, and then the window is opaque and doesn't let the light out. Okay, at that frequency range. All right. What do we know about Venus? Well, a couple really important measurements were made recently, a few years ago, that enable us to determine that Venus did have water on it, and maybe a lot of water. And so now we started the modeling process. We begin by the surface here. The colors are red and whites are the highs. The blues are the low areas. You create a model of Venus as a body, and then you put the water in it. Well, where's the water going to go? Well, the water's going to go in the lowlands. And now you let it evolve in the sunlight that you have at an early sun, and you just gradually increase it. Well, this is what we found out when we did that. Clouds form on the front of Venus, right at the subsolar point. And since Venus is a slow rotator, those clouds reflect a lot of light, and the water is maintained, okay? And so the water then that is heated circulates around the planet. And so this ends up being a place where life could have started. And it was like that up until about 800 million years ago, less than 1 billion years. Venus, we believe, was a blue planet. Pretty fantastic. Well, this is perhaps what it looked like. It doesn't look like that today. If it had a magnetic field, it doesn't have it anymore, and so it is sitting in the wind of the sun. During the time the sun now we can study, and the solar wind is pulling apart the atmosphere, And yet, Venus's atmosphere is pretty thick. It's 90 bar, where 1 bar is the Earth's atmosphere. To get 90 bar of pressure, you have to go in the ocean 1,000 meters. I mean, it's really deep. It's crushing depth. This is why it's always been hard to land on Venus and really study the planet. But we're planning to do that this next decade. We got a number of fantastic missions, and JPL is leading one that'll do that. Well, let's talk about Earth. So this is our special body. It has life. It's teeming with life. But did it teem with life all the time? And what about complex life? And when did that show up? And how does complex life evolve? And we may have some misconceptions about how that occurred, and so we want to tease that out a little bit as we look at it. So let's talk about the evolution of the Earth. As the collapsing cloud created the planets of our solar system, early on, the Earth was hit by another body that accreted in or near our orbit. And it was a large body. Planetary scientists call that body Theia. We believe that it was about the size of Mars. Okay, so it's a huge body. And that impact destroyed Theia and just ripped apart the Earth in many ways. And this is called the giant impact hypothesis. This was teased out from rocks we brought back from the moon in the Apollo program. Now, what happens after Theia forms, after the Earth reforms, is everything, let me go back one slide, everything beyond this blue line, called the Roche limit, can accrete into another body. Everything below this blue line will fall on the planet. Think of the rings of Saturn. All the rings of Saturn are inside the Roche limit. They're all destined to fall on the planet Saturn. Okay? So a new body forms, and this new body is the moon, and it forms really close to the Earth. You know, the moon today is at 60 Earth radii away. So it's shown here down the bottom slide. It's about how far away it is. And when it first formed, at about 4.5 billion years ago, it was only maybe 4.5 Earth radii away. And it's gradually drifted away. We know from the retroreflectors that the Apollo missions left on the surface of the moon, and we hit those reflectors every year with a laser. So why do we do that every year? Didn't we get it right the first time? Well, we're finding out the moon is moving away still. So the moon moves about 1.5 inches away from the Earth every year. So if you can imagine that time period, the moon, 4.5 billion years ago, it would be enormous. It'd dominate the sky. Okay, so as these objects cooled down, and this formed the moon, and it continued to move away, another process was occurring inside the moon. And it turns out the moon ended up with a magnetosphere. Okay, which is a magnetic field, a current that's running inside the moon. It's producing a fabulous magnetosphere. And so that magnetosphere is being buffeted by the very intense sun during that time period. And this is one of the things that we've been worrying about. You know, how could this Earth survive during the faint young sun when it was really active and the solar wind was just scouring potentially atmospheres away? Well, the moon may have played a role. Now, another event happened to the moon about the same time, and that's called what we call the late heavy bombardment, also determined from material brought back from the Apollos. Every time you have an impact in a region and rock melts and reforms, you actually can date that. You can date the beginning of that rock as it reformed, and then you can put together a picture of these impacts that occur. So these impacts were enormous on the moon. It's called during the late heavy bombardment. Now this blew away a significant part of the lunar crust, and magma flowed into that okay, from the lower crust, upper mantle. In other words, molten rock came in, and we can see the result of that by looking at the moon today and see the dark spots. Those were all huge impacts that have occurred, and that dark area is material that has come up, has a slightly different composition. That's why its color is a little different, and those are called the Mare, the lunar Mare. Now, what also happens is because that rocky material actually has heavier elements in it because it was dredged up from below, it also produced a change in the distribution of gravity on the body, okay? In addition to that, this is what's also going to help the tidal locking. You know, the Earth is going to pull on this massive material that we call mass concentrations that are on the moon and tidally lock it. But also, these areas are outgassing, all right? So the moon, 4 billion years ago, actually had an atmosphere. We think the atmosphere is probably twice that of what Mars's atmosphere today is. And the composition of that atmosphere has got to be from the volcanic material. And since the Theia and Earth combined to create these two objects, our volcanoes must be generating the same kind of material that the moon did early on. So it's going to be sulfur, and it's going to be all kinds of gases that are being come out, carbon monoxide, carbon dioxide, okay? So the moon had an atmosphere. Now that atmosphere and the magnetosphere, it held on to that atmosphere for a while during the time that the sun was really active until the moon's magnetosphere really died. Okay, the current stopped. It didn't have a huge core, so it was bound to die. And then the solar wind just took the rest of the atmosphere. It's gone, all right? All right? But during that time period, that atmosphere, just like ours, really precipitates out in the polar region. So it may have snowed on the moon, all right? Isn't that pretty neat? Now, what else is in these areas, in the polar areas? We call these permanently shadowed areas. These are huge cratered areas blowing material out. And as the atmosphere may have collapsed in these, it's going to have the lunar atmosphere in it. But the magnetic field between the Earth and the moon also brought the Earth's atmosphere to the moon. So we want to go to the South Pole. We could go to the north, but we're going to the South Pole, and we're going to core these permanently shadowed regions. And we hope to find all kinds of volatiles. And that will be the early history of the Earth and the moon, like we never had it before. And so that's a key step in understanding our evolution. But that's not where it stops. You know, the moon, yes, probably ran block for the Earth during the time of the faint young sun, but heavy solar activity with big winds, etc., helping preserve the lunar atmosphere as it did, but also the Earth's atmosphere. But it also stabilized our spin axis. Without the moon, the Earth's spin axis would be, called the obliquity, would be all over the place. Right now, it goes from 22 degrees to 24.5 degrees. Today, it's at 23.5 degrees, coming off 24 on its way to 22. It has a cycle for which the axis changes ever so slightly over tens of thousands of years, okay? But the moon has stabilized that. That has stabilized our climate in significant ways. And as it's moved out, it's slowed our rotation from 5 hours, which we expected. We think that's what it was when the moon and Earth came together after the Theia impact, to now 24 hours. All right? It's a wonderful set of time, day and night, that allows life to grow, recover, and obtain energy, to obtain food, etc. It also created tides. As the Earth was outgassing, perhaps some comets and meteors also contributed to the water on the Earth. We know comets have a lot of water. Turns out asteroids have a lot of water too. So the oceans on the Earth had tides. The Earth itself inside had these hydrothermal vents. Material is bubbling up in these hydrothermal vents. Perhaps life started there, and with the large tides back and forth, leaving life as it moves out from the hydrothermal vents up to the shores, enabling life to begin a process of becoming acclimated to the land. Perhaps tide did that. So what we then have is a moon that has really helped us be the life we have today, and without it, it would be hardly recognizable, be very different. So the moon may be an important contributor. Without the moon, current calculations indicate that the sun would have tidally locked the Earth by about 70%. So our day might have been 200 days long, okay? So the moon, it turns out to be really critical. Can we find moons around exoplanets? All right, that will be the next big step. Well, we have some indications, but we haven't really done a good job in that, but that's going to be the next revolution of our understanding of other solar systems, is finding the right planets with moons. And now we can put together the Earth's timeline of life. Here we have the Earth and the moon forming early on, 4.5, 4.6 billion years ago. Material that was bombarding the moon also bombarded the Earth, bringing water and also volatiles, all kinds of material to us, starting an environment where life could have got going, perhaps, as I mentioned, from the ocean through these hydrothermal vents. But Earth was not very hospitable early on. It really evolved. And the complex life that we're accustomed to today really is in the last several 100 million years. And when we look at the rock record, we see life coming and going. There's been 5 mass extinctions in the last 500 years. Now, this is complex life. Early on, we're talking about cellular life, really small, specialized cells that are dividing, evolving, and it's taken a long time for it to evolve into more complex life. Complex life has specialized cells. We have heart cells, brain cells, lung cells, all these different types of cells that have been created, giving us what we know today, complex life, all right? And our rock record talks about the mass extinctions. Well, what about that early life? Well, we'd like to know that spark where life started. What was the conditions like? Can we find it on Earth? Can we go back 4.2 billion years where it might have actually started? And the answer turns out to be no. And the reason why is the plate tectonics and the weathering has erased that era, that knowledge of the Earth that we would love to have interrogated to see what those conditions were like that may have started that spark that created life as we know. We can go to a couple areas that are old, like 3.8 billion years old. There's only a couple that old. One is Australia, and here we see microbial mats. These are stromatolites. These are single-celled mats that are coming together, and they're seen in the oceanic area, and it also helps potentially support the concept of life starting in the deep ocean and then moving to the land. But there's only a few of those around. So we think we understand what the history of the atmosphere of Earth has changed over time is like, but by going to the moon and doing these coring, this whole area is going to be refined. Now, why is that important? Because we're getting to the point where JWST and the next follow-on instruments that you're going to build and launch and deploy are going to start measuring the composition of those atmospheres of planets we want to know if there's life on it or not. So if we see a planet with this type of atmosphere, we can perhaps relate to that. We can perhaps say there might be microbial life but probably not complex life. And if there is some complex life, not like we know it today. So we really need to consider the evolution of our planets and what's happened. Now, the Earth has still maintained its magnetic field, and it still gets hammered by the sun. And these are the kind of studies that we're doing today, and that's try to understand the environments of other planets and therefore other suns. And these suns have all kinds of characteristics to them. Some are much smaller than ours with not much mass. Some are much bigger than ours with huge amounts of mass, and they all go through their evolutionary stage. And in a way, we have to know what's happening to really understand what the environments of those planets are. Well, we've got a magnetosphere still. We have a moon. That's helped us. So this is our starting point to really begin to make comparisons elsewhere. So magnetic fields, I'm a magnetospheric physicist, so I'll tell you they're important. Some of our people think too. But the bottom line is the sun also has a magnetic field, goes through a cycle. And that magnetic field produces a bubble we call the heliosphere. And that has protected us, we think, as the sun moves around the galaxy. Now, why is that important? Once again, we have to deal with this time dimension. It's not just looking at the Earth and seeing how it evolves over time with a sun that just sits and heats up. Okay, it's not that, because that whole system is moving around the center of our galaxy. Okay? And so what's that environment like? And we need to know more about that. We're just finding out that we have this bubble. We have some possible ideas. It may look like a comet, it may look like a sphere, it may look like a croissant, you know. And there's some good reasons why I like that croissant. But we have a couple probes that have now popped out of the heliopause, this area for which interior to that, the physics is dominated by the solar wind and the magnetic field from the sun, and exterior to that, then it's dominated by the interstellar medium. All right, so this is important to know. But we also realize that the sun is not in the galactic plane, okay? The sun is actually above the galactic plane. And the galactic plane is where all kinds of actions happen. Stars are being made right and left. There's clouds of material from explosions that are occurring. And planets are being generated around those new stars. And we're just above that, and we go through a cycle where we're pulled down to the galactic plane. And we overshoot that, and we come back out. And that cycle is 70 million years. And that cycle allows us to come in and out of that environment. And in fact, what it does is it means we move through clouds of material. And the clouds of material affect the size of our heliosphere. And it may be the case that our heliosphere, which is like 120 astronomical units away, it's just a huge little bubble, may have gotten less than the distance from the Earth to the sun, which is 1 astronomical unit, pushing our planets from Earth on out into the interstellar medium. And what we know about that environment from the Voyagers is that the heliosphere has protected us from what we call galactic cosmic rays, high energy particles that are generated in many different processes, supernova and many others, we're sure, and how that affects our atmosphere and what happens to us during these time periods, we're not quite sure. But we can model this. We need to know about that, but we can model this. But we think as we move through molecular clouds with significant hydrogen content, that provides a major problem as our planet plows through those clouds, and molecular hydrogen comes in the form of water and hydroxyl, and can actually destroy ozone. And there seems to be some indications that occurred when we look at amber on about 65 million year basis, when we were, once again, moving through the galactic plane. So how all these things tie together, we're not quite sure. But we do know, I think, understanding this is important because we have to factor that into the habitability of other planets around other stars that are doing some other things, coming in and out of the plane or staying in the plane or being in a big molecular cloud. And maybe that's the determining factor of what happens on those planets relative to the life that may or may not be there. Okay, so now what about Mars? Well, Mars is further away from us, and it has quite an axial tilt, all right? Its obliquity, we call it, seems to be all over the place. Why is that? Well, Mars is an object that's formed, and when we think of, oh, Earth is nice and spherical, and that means the mass is distributed evenly, and that's the wrong idea because it's not. You know, there are lumpy areas on the Earth just as they are on Mars, and the gravity from the sun just yanks on those and causes the body to lay over. You'd be pushed by the material where the mass is. Okay, so the obliquity of the Mars axis, rotational axis, has gone from 15 degrees up to 48 degrees. I mean, it's from what we can tell, just in the last 10 million years. So this is really significant. Can you imagine the climate change that's been going on Mars alone? Okay, and it's been like that. It has no moon to stabilize it. Here's the variation of the Earth compared to the variation on Mars, compared to how the climate might change just in their polar caps. It's a huge effect. What we know about Mars is indeed Mars also had a significant amount of water. We're running around Mars now with our rovers, and we're finding all kinds of minerals that were made with water. Okay, and this is just a fantastic time in the past, and but something happened. Huge climate change occurred, and Mars became more arid. But Mars doesn't have much in the way of plate tectonics, and if life started on Earth and started also on Mars about the same time, that spark and the environment that occurred may actually be there available for us to go and find and look at that record and get an idea of what it was like when life really started on these planets. Now, with that said, I can easily tell you there's no life on the surface of Mars, but there may be life below the surface. Now, Mars doesn't have a magnetic field anymore. It did, but it's also being scoured. And its atmosphere is now down to about 1% of our own in terms of its mass. It's largely CO2, and yes, a greenhouse effect does occur on Mars. It heats up Mars a little bit because of that CO2 is a greenhouse gas. It has water vapor in the atmosphere, but it's also got nitrogen and argon and a number of other trace elements. So Mars has got a lot of possibilities to it because with our rovers, now down on the surface, we can make all kinds of measurements. Now here are the ones that have landed, like the Viking Pathfinder, Spirit and Opportunity, the Chinese Tiwan, and Insight. Those and Phoenix no longer are working, but they've landed and made some fabulous measurements, and we really understand what's happening. This is a Mercator projection of Mars. The coloring tells us the height. The white and the red are the highs. The blues are the lows. And if you take a massive amount of water and dump it on the planet, it's going to be in the blue areas. Now, where we land is in the green areas. That's the ancient shoreline for Mars, okay? That's where we want to go. Perhaps life moved from the ocean and entered the land in some way. You know, that's what we think here on Earth. Perhaps that happened on Mars. And so many of the things that we're doing takes that into account. We landed with Curiosity in 2012. It has a drill on it. And that drill is actually like a straight screwdriver that hits the soil and then turns and then hits the soil and turns and just grinds it all up, all right? The size of these holes are about the size of a dime. And these are the first 2 holes we drilled on Mars. And wow, we loved it. These are not red. The patina on Mars is red everywhere. This is gray Mars. Below the patina of red, oxidized surface, are really nice soils. So we can scoop that in and taste it, and we find it's got carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Does that sound familiar? Okay, all the right stuff. Things that we see between these two fingers. All right, as soils are moist, and there's nitrates in them, which is also great for fertilizer. Okay? So Mark Watney, can you grow potatoes? Or not? Well, you have to add a few things. But in any event, this makes it a really nice environment, so we know a lot about it. Another thing that Mars has is methane. We've observed methane coming from Mars for a while with telescopes, and now we're sitting on the surface, and the methane's coming right through the surface. This is fantastic. 95 or more % of the methane here on Earth is generated from life. But unfortunately, methane is a nice biomolecule, could also be generated abiotically. You need olivine and a hot source, which would be magma and water. And we know Mars has got water all over the place in the crust and below. And so methane can be generated, all right? And so Mars goes through this cycle where methane is being generated all over the place. So Mars may actually have had life. And as the climate and things get extreme, life loves to go into the rocks. And so, I asked Mary, how much life do we have here on Earth and where is it at? And the astrobiologists tell us there's more biomass below our feet of life than there is that's walking on the surface of the Earth or in the ocean. All right? Life has got a hold of this planet like crazy. That may be the case at Mars, all right? Even though it's been arid for 3 billion years, no water on the surface for that long, there may be life below the surface. It may be in aquifers, okay? But it also may be on the way out, all right? So we want to be able to understand where this is coming from and whether this is a life signature or not. Our other rover is Curiosity. And Perseverance. And we landed Perseverance, and the concept behind Perseverance is we need this rock record. We need to go back in time on Mars. We need to understand what's happened. And we're going to go to an area that is an ancient delta. Okay? So imagine drying up the Mississippi, getting rid of the Gulf of Mexico, looking at the Earth. You see this huge delta down there where New Orleans is, and that structure, that feature is exactly where we are on Mars. In fact, there's probably 2 rivers that dumped into this crater called Jezero. So we core rock. So here's a core. This is one of these cores. It's a nice circular core. And then we put it in a sleeve. Here's one of our sleeves. And what we've been doing is laying them down on the ground, okay? Because we want our rovers to come and pick it up, or any other nation that works with us, and bring these samples back. Now, what are we going to do when we get these samples? Well, once again, it tells us what's going on in the evolution of the planet. Let me give you an example. On Earth, there's 5,000 plus minerals on Earth. 337 of them are made with dead life, okay? Can't make the minerals without dead life. And so the rock record is going to tell us in this delta, where if we look at our own ancient deltas, teeming with dead life in the past, that we may have some examples of life in the past on Mars. So we need to bring these samples back. It's going to tell us about the evolution of the planet. It's going to get us at a time when we want to understand how life may have started, and it may actually demonstrate there was life on that planet. So these samples are really critical for us. Now we're struggling with how to come to a process to go get them, but I guarantee you we're going to go get them, and we're going to bring them home, and we're going to analyze them. All right? And we're going to do that in my lifetime. That's my pledge. All right. But let's look at what happens to Mars over time. Going forward now, what's going to happen to Mars? Well, here is its north polar cap. This is sitting in this blue area, so it's lower than the rest of the planet. Okay, so water was all over this area. And in fact, this is really a huge polar cap. We can study it with radar and get a nice height distribution of it. And we see it's huge. And in fact, we can take an estimate of the amount of water that's in it. And it looks like 1/7 of the ancient ocean of Mars is probably trapped in this polar cap. Now, it's got a veneer of CO2 over it, okay? It's got a veneer of CO2 over it. Well, here we are on the chart. As the sun heats up, the CO2 is going to start sublimating. And as the sun continues to heat up, we hope that some of this water will melt. Now, Elon wants to nuke it to get the water sooner. Let's not do that. Okay. But conceptually, Mars may end up with water on its surface at a time when the heat from the sun continues to increase. And it may look like this. Now, that's in another 800 million years, so it'd be great to stick around that long. But in any event, now we can put together a better picture of what's happening and what's going on with this, once again, habitable zone over time as it moves out. But we need to not think of the habitable zone. We need to think of a habitable state. Okay, Mars was a blue planet, Earth was a blue planet, Venus was a blue planet, when the habitable zone was more centered at Venus than anything else. And yet life started on Earth and may have started on Mars. So here we are. This is too hot. This is too cold. Here's where Earth is. This is the age of the sun. And this is the habitable state we're in now. Mercury never had a chance. Venus may have gone through a habitable state. Earth actually almost became too cold. There's a couple climatic events that occurred on Earth, whether we're in the heliosphere or out of the heliosphere at the time these occur, or is hotly debated, okay, for which we almost popped out and became too cold. And we call that era snowball Earth, where we had ice everywhere, all over the planet. But we stayed in the habitable zone. And when we become too hot, we better be on Mars. Because Mars may end up being the habitable planet of our future. So when we look at planets around other stars, we have to think about the habitable state. We need the information about the climate in addition to the information about the heat from that star to determine where that habitable zone is and how those planets are situated in a habitable state. So we're now settling down on some really important and key sets of information that we're going to go after. So here's the habitable zone over time. It's going to move away from the Earth and on out as the sun goes through its hot phase. And for decades, planetary scientists had this concept of being in a location where you could have water, and any place beyond this location in the solar system, water must be solid. It must be frozen. And we called that location the snow line. So here's the snow line, and for a long time the thought was anything beyond the snow line is going to be water, it's going to be frozen, okay? Boy, were we wrong, okay? And the reason why is we're finding moons around these giant planets that have oceans in them. These are fabulous moons, and that we're launching a mission to go study them. The next one is called Clipper. It's going to launch this October. JPL is building it, doing a fabulous job. And it's going to go to Europa, and it's going to look at the habitable state of Europa. We're going to really tease out how thick that ice shell is and what's below it. Well, how does this happen? Okay, Jupiter's an enormous planet. How does it get moons that may have water on them? Well, here are the 4 Galilean moons. All right, Jupiter is off to the left. It's tidally pushing on all these planets, squeezing them with its tidal forces. Jupiter is 300 times the mass of the Earth. 300 times the mass of the Earth. All right, And so these moons are on the order of the size of our own moon. Io is just about the size of our moon. And in fact, Ganymede's the largest moon in the solar system. Ganymede has its own magnetic field. Wow, love that body. And Europa, I can't see a crater on Europa. Io's got all these unusual looking features. There's some craters on Ganymede, and Callisto's just full of craters. Why aren't these moons looking identical? They were all made at the same time. It's tidal forces from Jupiter. The closer you are, the more Jupiter squeezes you, that has changed the geology of the planet, or the moon rather. Io had an ice shell. It formed perhaps just like Europa, but it's too close to Jupiter, and as Jupiter squeezes Io, that heat dissipated the ice shell. Now, how does it squeeze it? Well, these moons are in elliptical orbits, which means there's a part of the orbit that's close to Jupiter, and then there's a part of the orbit that's further away. So you go close to Jupiter, you go further away, you get released. Back and forth and back and forth. And that heat's got to go somewhere. And you melt the rock, and at any one time, Io's got 100 volcanoes on it. It's the most volcanically active body in the solar system. And what about Europa? Well, Europa is this beautiful moon with hardly any craters on it, which means the ocean underneath it, now that we know the ocean is there, must have communicated to the surface and filled in all the craters. That's why it doesn't have any craters. And the ocean is about 100 kilometers thick, we believe, under this ice shell. Now, the tidal forces on Europa aren't as bad as Io, but it does get squeezed, it does get released, and the surface of Io moves 30 meters every 2.5 days as it orbits Jupiter. 30 meters, yeah. So it's going to melt that ice, but it's not strong enough to dissipate the ice shell. So what we think is at the bottom of these oceans are hydrothermal vents. So if hydrothermal vents are at the bottom of Europa's ocean, is that also the environment for life? Well, it looks like it's got the water, that's for sure. It looks like it's got the organic chemistry. The tidal forces form the energy. So it's got all the basic ingredients. And so maybe there's life in the Europa ocean. There's no reason to think that it can't be complex, because this moon has been like this for billions of years. Okay, now it's gone through a number of changes, but indeed, time is on its side to create complex life. Saturn, we got another moon, fabulous moon, Enceladus. It's much smaller, but it has all the basic features too. Titan's another moon, okay? Now, Titan is the only other body in the solar system that has liquid on its surface. And that liquid is not water, it's methane. But it is a liquid. And so what about the possibilities? And it's got all the organics up the wazoo. You know, it could be completely different life than we're aware of. And maybe you saw the wonderful episode about the Horta, which was life like we don't know. Wasn't carbon-based, it was silicon-based. All right, we want to go there. We got a mission called Dragonfly. So all these beautiful ocean worlds, we believe have water layers in them. And we want to explore them, and they're moons of Jupiter, Saturn, Uranus, and Neptune. All right? Well, what about exoplanets? All right? Now we're going to take what we've learned and very briefly touch on what we see out there. Well, with Kepler, this is a fabulous telescope where as the planet moved in front of the sun, the light just dimmed ever so slightly and then left, and then the light came back, and we monitored 120,000 stars constantly for a couple of years. We found thousands of planets, okay? And so when you look at that and you tally it up, what do you think the most popular planet is? Well, I always thought, oh, it's going to be Jupiter. No, it's not. Here's Jupiter, okay? Here's Earth-sized planets here. What we see, the most popular planet seems to be super Earths and mini Neptunes, all right? Well, we don't have a super Earth. We don't have a terrestrial body that may be 10 times the mass of the Earth. Now, that doesn't mean it's 10 times as big, because it'll crunch down to maybe one and a half the radius of our Earth. But the bottom line is, we don't know how it's structured, whether there's oceans or atmospheres on it. We really need to tease that out, so it's a huge area to explore. And of course, we're starting that process with these beautiful telescopes like Webb to look at the atmospheres. And we're going from detecting these planets, that knowing they're there, to detecting the signatures in their atmospheres that could potentially tell us about life. And of course, does this spectrum look like the spectrum of Earth today, or the spectrum of Earth in its past, or the spectrum of Mars in its past? These are the kind of things that we need to start comparing against so that we understand the state of the evolution of each of these moons and whether they could harbor life or not. And of course, what we're looking for are some really neat signatures, biosignatures, methane. And oxygen, we have oxygen on this planet. There's 70% of our atmosphere is nitrogen. It's only the rest that's oxygen. So even a little oxygen makes a big deal. And so we want to look for those things. But we shouldn't forget the rogue planets, because they could be Jupiters, and they could have moons. And those moons may be icy bodies with oceans, all right? So it's not just about the orbiting the stars. The energy now that we're looking at from tidal forces may indeed mean that these are important too. Now, when we look at the exoplanets that are orbiting stars, we want to have high enough resolution to look at the planet itself when it comes out from behind it and when it goes in front of it. And in these areas, we want to look at the atmosphere to really tease out any trace gases of importance, maybe gases like CFCs that are made by humans on this Earth. Maybe there are chemicals that aren't indigenous to these atmospheres. Chlorofluorocarbons, who knows? We'd have to warn them that's not a good idea. But in any event, all these signatures could tell us, perhaps, if there's intelligent life on those. When you look at the Earth, and we see the artificial light, and we see the additional heat, and we can make measurements of Earth, we want to get to the point where we want to look at those planets on the night side too. So we're not only after the status of the planet relative to what kind of life it might have, from microbial to more complex, but whether there's intelligent life there too. So, in ending, when you look out tonight, because it was clear today, I'm sure it's going to be clear tonight, and see the stars, think of the planets that are orbiting them, because they're everywhere. And think about what we're going to learn in your lifetime. I think in your lifetime, we're going to be able to answer the question, are we alone? Thank you very much.